How in the world do multiverse scientists justify the real existence of infinitely many universes?
They do this with eternal inflation, a theory that actually leads to the creation of an infinite number of unobservable parallel universes. We'll explain the science behind eternal inflation and show how it naturally follows from the real scientific problems that motivate the mainstream theory of cosmic inflation.
This episode will have more scientific details than any other episode in this series. So if you start feeling like it's just too much heavy science, feel free to skip ahead to the next episode, where everything starts getting much easier.
Skip ahead, but they miss out on such great physics.
I know you love physics, Aaron, but complicated physics isn't for everyone. And it really isn't necessary for understanding multiverse theory and seeing why it goes wrong. Even if you accept that multiverse scientists have provided scientific justification for an infinite number of other universes, the rest of this series will clearly show why the multiverse is a bad theory that's totally incapable of explaining fine-tuning without an intelligent cause.
You're right, Ellie. This episode is harder than the rest of the series. But if you don't skip it, I think the payoff will be worth it. You'll get a first-hand glimpse into the fascinating physics behind the modern and updated version of Big Bang inflationary cosmology.
Welcome. This is Physics to God, a guided journey through modern physics to discover God. Eternal inflation is one of the most popular scientific supports for the multiverse. To lay the groundwork for understanding this support, we'll begin with the basic theory of inflation, a theory first proposed by Alan Guth in 1979 as an important modification to the ordinary way physicists understood the beginning of our universe, otherwise known as standard Big Bang cosmology.
According to standard Big Bang cosmology, the universe started with all its energy concentrated at one point in space. After that first moment, the universe began to expand. Scientists assume that the universe has expanded at a relatively constant rate since the first moment of the Big Bang.
This intuitive premise led to a few problems. While Aaron will explain some of these problems in complicated physics terminology, and I'll give simple analogies to help you understand what he's talking about, you should know in advance that you don't need to follow the details of these problems or their solutions. We just wanted you to have a basic idea of what inflation means and the problems that motivate it. Aaron, why don't you try to clearly explain two of these problems?
Sure, Ellie. One of the difficulties is the horizon problem. Whenever scientists examine two distant places in the universe on large enough scales, they always find them to be around the same temperature. This would make sense if these places, which are currently billions of light years apart, were once in contact with each other. Such contact would have allowed them to acquire comparable properties.
This would be akin to a cup of hot water eventually becoming the same temperature as the room that it's in.
However, according to standard Big Bang cosmology, there was never a point in time after the Big Bang when they were in contact.
To help appreciate this problem, consider an analogy involving temperature on Earth. We can readily understand why two very close places on Earth would have approximately the same temperature. However, you would be very surprised if we were to discover two places on opposite sides of the globe that were always the same temperature. Yet, this is comparable to what we observe when looking at the universe in all different directions.
It's a bit more complicated than this, because you may be wondering why the common origin of the Big Bang doesn't suffice to coordinate their temperatures. Going into the details to answer that would take us too far afield, but the short answer is that quantum gravity effects in disconnected regions immediately after the Big Bang should have caused them to have randomly different temperatures.
Remember, Aaron, we're not trying to teach complicated physics here. For our purposes, it's enough to understand the basic problem cosmologists face. Why is it that on large enough scales, we observe all places in the universe to be at roughly the same temperature, no matter where we look? What caused the temperature to be so nearly uniform? Now, Aaron, could you please explain the second problem?
The second difficulty is the flatness problem. The basic problem is to explain why the shape of the universe is so close to being perfectly flat, without any random bumps or curves. It's almost like it was intentionally made to be perfectly flat, something that physicists wouldn't have expected without observing it to be so.
It's difficult to fully comprehend this problem because it relates to the geometrical shape of the three dimensions of space. For the sake of simplification, you can picture the problem by thinking about a two-dimensional space instead. For example, consider a bedsheet. If it were randomly thrown down on a bed, we would expect it to have wrinkles and bumps. If we instead found it to be perfectly flat, we would look for a cause that made it that way. Analogously, physicists were looking for the cause of the universe being so flat.
The theory of inflation proposed by Alan Guth modified standard Big Bang cosmology to solve both of these problems. The main idea is that the very early universe underwent a short period of very rapid expansion, and only afterwards slowed to the moderate expansion we observe today. This inflation is proposed to have occurred within the first second of the universe's existence, and to have lasted for only a fraction of a second. Nevertheless, the tremendous expansion in that short time had significant implications.
You can think of the universe's expansion like you're inflating a big balloon. The theory of inflation suggests that instead of inflating the balloon at a constant rate, you inflate it a tremendous amount in a very short period of time when you first start blowing it up. After that, you continue to inflate it at a relatively slow rate.
This helped answer the two problems. First, inflation answered the horizon problem. Why do any two places in our observable universe have the same temperature? This is because all places in the universe we observe, no matter how far apart they are now, were in close enough contact after the Big Bang but before inflation occurred. The time they were in contact was sufficient for them to attain the same temperature. Even after inflation occurred, this equivalence was roughly retained until today.
To help visualize this, imagine you have an uninflated balloon and you mark off 2 points separated by a centimeter. Then you inflate the balloon to be 1,000,000 times bigger. Those 2 points would now be much farther apart than before. Similarly, 2 points in the universe that are now very far apart were much closer together before inflation occurred. At the earlier time, they would naturally attain the same temperature, just like a hot cup and the room it's in. Even though the universe's rapid inflation subsequently caused a rapid increase in the distance between them, it's perfectly reasonable that they would retain the same temperatures.
The theory of inflation also explains the apparent flatness of space. This is because no matter how bumpy and jagged the initial shape of space was, extremely rapid inflation would smooth it out so that space would look almost perfectly flat today.
Returning to the balloon analogy, compare 2 balloons, one slightly inflated and one inflated to a massive size. On the slightly inflated balloon, a small area on its surface will appear curved. But on the massively inflated balloon, a small area on its surface will appear like a flat bedsheet. This is like the fact that we don't see the curvature of Earth when we walk down a city street. According to the theory of inflation, the universe is like a massively inflated balloon. It looks flat because everywhere we can see is only a small portion of the massively inflated universe.
Besides the theory of inflation's solution to these problems, it has also made quantitative predictions that were confirmed by observation. That is, it predicted the distribution of energy that we observe in the cosmic microwave background radiation with impressive accuracy.
The background radiation is a faint, non-visible light that scientists can observe now, but originated at a very early stage of the universe. This light is one of the main data points that scientists use to compare their theories of the early universe against real data.
The theory of inflation predicted the observed patterns in the background radiation by applying quantum mechanics to the early universe. Before the rapid expansion, the universe was very small, with all its energy close together, and therefore approximately the same temperature and homogeneous. However, due to quantum mechanical fluctuations in the very small early universe, the theory predicted that the energy density wasn't exactly the same everywhere. And it turned out that the patterns expected from those fluctuations were precisely the patterns scientists observed in the background radiation.
While that sounds fascinating, I won't even try to make an analogy for that. The main point is that the theory of inflation made a quantitative prediction that was confirmed by observation.
I do want to mention that this evidence is not a smoking gun in favor of inflation, because there could be other ways to explain these patterns, and we'll even discuss some of these alternatives in later episodes. Nevertheless, it's considered significant support and shows that inflation is a real scientific theory capable of making testable predictions.
Aaron, while I'm sure many of our listeners found this whole inflation discussion very interesting, or very complicated, they might be wondering what in the world our one universe's rapid inflation has anything to do with the infinitely many universes of the multiverse. Remember, Aaron, our show is Physics to God, not physics to more physics.
Ellie, you have to have patience. We're going to get there. Sort of. If you noticed, the theory of inflation as we've presented it so far is just a description of something that happened to the early universe, that it expanded a lot very quickly. However, that description doesn't tell us what caused inflation to occur in the first place. In other words, what was the mechanism that caused the early universe to expand so quickly?
Okay, I hear that question. So what was it?
Well, scientists don't exactly know that, but they have a lot of different ways of modeling possible mechanisms that caused inflation. And it's only when we consider these models that the multiverse becomes relevant.
So it sounds like there are two different things here. First is the theory of inflation, which is a description of something that happened in the early universe. Second are the various ways to model the mechanism that caused this inflation.
Right, and that's the key point. There's the theory of inflation that has supporting evidence from observations, and then there are various models of inflation which don't.
To illustrate this crucial difference between a theory and the various models for a mechanism that explains the theory, consider the following analogy. We take a cup of hot water and place it in a cold room. After a sufficient amount of time, we'll find that the water is at the same temperature as the room. Generalizing this observation, we can develop a theory. Whenever two objects of different temperatures come into contact with each other for a sufficient amount of time, they end up at the same temperature. This is called thermal equilibrium.
Whoa, thermal equilibrium? Are you trying to confuse people, Ellie?
I guess you're rubbing off on me, Aaron. Now, despite this basic description of the theory, we still haven't provided the mechanism that brings the water and the room to the same temperature. We can propose several possible models, each describing a mechanism for producing this result. 1. The heat in the cup flows out of the cup into the air of the room, causing the cup to lose its heat. A second model, the reverse. The coldness of the room flows out of the air into the cup, causing the cup to cool down. And yet a third model, some combination of heat and cold exchange between the cup and the room caused them to attain the same temperature. These represent 3 of the many possible models.
Hey, what about 4? Temperature is related to motion, and the particles in the cup and the room bump into each other many times until they arrive at the same amount of average motion per particle, which happens to be the actual explanation of modern physics.
Sure, Aaron. We can add that one too. I'm sure that makes my analogy much clearer for everyone. These represent 4 of the many possible models consistent with the observation that the cup and the room eventually attain the same temperature. Now let's assume that we perform many experiments to test the validity of the theory that whenever 2 objects of different temperatures come into contact for a sufficient amount of time, they end up at the same temperature. For instance, we can place many hot objects next to many cold objects to determine if they always end up at the same temperature. If they repeatedly do, then we have empirical evidence that our theory is correct.
I do this experiment every day with a hot cup of coffee, and I can tell you, Ellie, that it eventually gets to room temperature.
That's a nice little tidbit, Aaron. It's a bit random, but at least you're trying to give a helpful analogy. Let's return to all the experiments, including Aaron's cup of coffee. They all support the theory that whenever 2 objects of a different temperature come into contact for a sufficient amount of time, they end up at the same temperature. The question becomes, which of the 4 models does all this evidence support?
The answer is none. Any of the models can equally explain all these experiments. The crucial point is that proof for a theory is not proof for any particular model.
To find support for a particular model, we would need to construct some sort of critical experiment that would differentiate between the different models. Only then can we determine if there's evidence for any particular model of the theory as opposed to all the other models.
Just as there are many models for the mechanism that brings about thermal equilibrium, there are many models for the mechanism that brings about inflation. In fact, there are around 100 competing models for inflation.
And just like in my analogy with the hot cup in the room, the evidence in favor of the theory of inflation doesn't constitute evidence for any particular model of inflation.
Keeping in mind this distinction between the theory of inflation and its many models, we're finally ready to see how the multiverse becomes relevant.
The main idea is that some models of inflation lead to one universe and others lead to an infinite multiverse.
Right. Many models of inflation, in fact most of them, lead to the surprising conclusion that if inflation happens once, it will keep happening in different regions of space over and over again. As those separate regions experience inflation, this naturally leads to an infinite number of separate bubble universes, most with no possibility of ever coming into contact with the others.
These models of inflation are collectively called eternal inflation. Roger Penrose, in Fashion, Faith, and Fantasy, explains as follows. There are various extensions of the original inflationary ideas, the most influential going on their names like eternal inflation. The general idea of these proposals seems to be that inflation can be set off at various places throughout space-time. Such regions are often referred to as bubbles, and it is supposed that our own perceived universe region is such a bubble. In some versions of this kind of proposal, it is envisaged that there is actually no beginning to this activity, and it is normally taken that there is to be no end.
If the eternal inflation models are correct, then scientists have strong support for the infinite multiverse premise. However, other non-eternal models of inflation only involve finite inflation and only have one universe that inflates shortly after the Big Bang. If these models are correct, then inflation has nothing at all to do with the multiverse.
The point is that both types of models, eternal and non-eternal inflation, are entirely consistent with the theory of inflation described earlier. All the problems that the theory of inflation solved, and all the observations that support the theory of inflation apply equally to all models of inflation. Those that generate an infinite number of universes, and those that only yield our one universe. As such, it would be inaccurate to claim that the theory of inflation itself establishes the infinite multiverse premise. Brian Greene, in The Hidden Reality, expands on this point as follows. Astronomical observations over the past decade have bolstered the physics community's confidence in inflationary cosmology, but have nothing to say about whether the inflationary expansion is eternal. Theoretical studies show that although many versions are eternal, yielding bubble universe upon bubble universe, some entail but a single ballooning spatial expanse.
Nevertheless, supporters of eternal inflation argue that the simplest, most natural, and least fine-tuned way to model inflation inevitably leads to eternal inflation and an infinite number of bubble universes. Therefore, even though all the evidence for inflation equally supports both finite and infinite models, they argue that we should choose an infinite model over a highly contrived finite model. Greene explains as follows. There are versions of the inflationary theory in which inflation is not eternal. By fiddling with details such as the number of inflaton fields and their potential energy curves, clever theorists can arrange things so that the inflation would, in due course, be knocked off its perch everywhere. But these proposals are the exception rather than the rule. Garden variety inflationary models yield a gargantuan number of bubble universes carved into an eternally expanding spatial expanse. And so, if the inflationary theory is on the mark, and if, as many theoretical investigations conclude, its physically relevant realization is eternal, the existence of an inflationary multiverse would be an inevitable consequence.
There is certainly merit to this argument. Assuming one accepts the theory of inflation, it's reasonable to extrapolate from the laws of physics in our universe by modeling inflation in a manner that is mathematically simple and minimizes extra assumptions.
This is proper methodological thinking and is a legitimate application of Occam's razor. If there are many different ways to model something, the simplest model is the best and often the correct model to choose.
Since the simplest models of inflation lead to an infinite number of bubble universes, eternal inflation provides multiverse scientists with their best support for the infinite multiverse premise.
Even though the theory of inflation is a scientific theory supported by observations, and even though the simplest way to model inflation leads to eternal inflation, positing an actual infinite number of intrinsically unobservable universes to explain our one universe is a dubious proposition.
As we discussed last episode, eternal inflation takes a stand on the controversial issue regarding the existence of an actual physical infinity.
More importantly, an infinite number of actual universes creates major problems for multiverse scientists' attempts to establish the third premise, that our universe is typical, and leads directly to something called the measure problem.
Don't worry about this for now. We'll discuss these issues much more in later episodes.
While most cosmologists accept the theory of inflation and the infinite number of universes that come along with eternal inflation, there are a few notable scientists, among them Roger Penrose and Paul Steinhardt, who maintain that there are better alternatives to explain the observations that the theory of inflation claims as supporting evidence. We'll discuss their theories in more depth in a later episode.
The point is that even the basic theory of inflation hasn't been conclusively proven. At this point, it's merely mainstream cosmologists' best explanation for our observations. Physicist Paul Steinhardt, one of the originators of the theory of inflation, in his book Endless Universe, elaborates on this point. He says as follows: "This raises a provocative question. Is the inflationary model, as it currently stands, a valid scientific theory? Or is the discovery of infinite possibilities a sign of a serious flaw, both logically and scientifically?" A poll of cosmologists today would probably reveal that an overwhelming majority believe inflation to be not only a valid idea, but the most likely explanation for the universe we observe. But if the poll went further to ask whether the infinite number of possible universes is a problem, it would probably reveal a split into very different camps.
It's important to note that no scientist posits an extremely large but finite number of universes, a functional infinity, to rescue inflation from the problems of actual infinities that we'll discuss in detail later. This is because one can't legitimately posit other universes besides our own without demonstrating that the known laws of physics of our universe naturally lead to the generation of these other universes.
But, as Brian Greene pointed out, garden variety inflationary models yield an actually infinite number of universes, and there's no way to make the number of universes finite without artificially rigging it in a totally ad hoc manner. Since no known laws of physics naturally predicts a large but finite number of parallel universes, and because non-eternal inflation models with only one universe are highly contrived, the only reasonable scientific choices are eternal inflation with its infinite universes or a different theory besides inflation.
Notwithstanding the prior points, let us grant multiverse scientists that the theory of inflation has been well established and that the best way to model inflation results in an infinite number of universes.
The question is, would this alone provide sufficient support for multiverse theory as a complete explanation for our designed, fine-tuned, and ordered universe without the need for an intelligent cause?
The short answer is no. At best, inflation supports the infinite multiverse premise and points to the existence of many fine-tuned universes, but does nothing to support the existence of a varied multiverse.
Recall, for a multiverse to explain fine-tuning and design, multiverse scientists must show that the laws and constants of nature vary from universe to universe. Not only does eternal inflation fail in this regard, it seems to undermine the varied multiverse premise, and instead indicates that each of the bubble universes is designed and fine-tuned just like ours.
The reason is as follows. Since eternal inflation relies on the known laws of physics to derive the existence of other universes, it naturally follows that the unobservable universes suggested by eternal inflation would have the same design laws and fine-tuned constants as our universe.
Brian Greene explains this point as follows. All the same, we can still contemplate an imaginary voyage to one or more of the other bubble universes. On such a journey, what would you find? Well, because each bubble universe results from the same process, the inflation is knocked from its perch, yielding a region that drops out of the inflationary expansion. They are all governed by the same physical theory, and so are all subject to the same set of physical laws.
Despite the general point that the laws of physics and almost all the constants should naturally be the same in the different bubble universes, Greene argues that there is one exception to this point, the Higgs field that allows particles to have a mass. He writes, in many versions of inflationary cosmology, a Higgs field would naturally have different values in different bubble universes. This wouldn't technically be a change in the fundamental laws of nature, because the Higgs value is different from the other constants of nature. It gets its particular value from spontaneous symmetry breaking. Therefore, it's not logically necessary that the Higgs value remain the same in all universes.
Whatever that all means. The point is that even assuming eternal inflation's infinitely many universes, the laws and all the other fine-tuned constants that we mentioned in episode 3 of series 1 should naturally be the same in all the universes. Therefore, to explain fine-tuning without an intelligent cause, multiverse scientists must still provide support for their premise that the laws and constants vary from universe to universe.
Before moving on, we'd like to point out that even though eternal inflation cannot address the design of the laws and the fine-tuning of the constants, unless it also shows that the laws and constants vary from universe to universe, eternal inflation does make progress towards explaining the ordered initial conditions of our universe.
This is based on the fact that even in our universe itself, the specific arrangement of space, time, and matter isn't fixed, but constantly changes. This being the case, there's no reason to think that all of the bubble universes in Eternal Inflation's infinite multiverse started in the exact same initial state. Rather, it's reasonable to assume that they each started with different initial conditions. Since some of these would be as highly ordered as our universe, the infinite universes of Eternal Inflation would seem to avoid the indication of an intelligent orderer regarding the initial conditions.
That being said, in later episodes, we'll explain how problems involving infinities lead to the eternal inflationary multiverse's failure regarding our universe's highly ordered initial conditions as well. As you might guess, positing an infinite number of unobservable universes has many strange consequences and causes very serious problems. In fact, these problems lead directly to the devastating measure problem, a problem that completely undermines multiverse theory.
But you'll need some patience until we get there. For now, despite our reservations about eternal inflation, for the sake of argument, let's work with the assumption that eternal inflation is correct and temporarily assume that multiverse scientists can use it to meet the burden of proof for the infinite multiverse premise. We're only going with this because we want to show that the multiverse fails to be a good scientific theory, even in multiverse scientists' own framework.
Even if we grant eternal inflation, recall that this only points to infinitely many universes that are all designed and fine-tuned. In order to provide evidence that the laws and constants vary from universe to universe, and thereby explain design and fine-tuning without an intelligent cause, multiverse scientists need other arguments.
In the next episode, we'll discuss the shocking hidden premise that multiverse scientists harbor, and show how they use this hidden premise to justify the claim that the constants vary between universes. And trust me, the next episode will be much lighter on the physics.
While it'll be lighter on the physics from here on out, the rest of this series will be even more fascinating. The craziest, wildest, and honestly most entertaining ideas are still yet to come, so stay tuned.